Welcome to AP Precalculus, where today we'll be exploring a fundamental concept, equivalent representations of polynomial and rational expressions. Understanding this is crucial because the way we write an expression can tell us different things about it. By the end of this video, you will be able to rewrite expressions in different forms and understand why you would choose one form over another. Specifically, our learning objectives are to rewrite expressions into forms useful in context, and to use polynomial long division and the binomial theorem to achieve these forms. Let's start with polynomials. The most common forms are standard form and factored form. Each one reveals different key features. Let's begin with standard form. In standard form, we write the terms of a polynomial from the highest degree term to the lowest. For example, f of x equals 2x to the fourth plus 3x cubed minus 5x plus 8. This form's primary strength is showing us the end behavior of the function. The end behavior is determined by the leading term, which is the term with the highest degree. Here, it's 2x to the fourth. The coefficient, which is 2, tells us if the function opens up or down. Since it's positive, the graph will rise to the right. The degree, 4, tells us the number of turns the graph can have, but more importantly, an even degree means the ends of the graph behave the same way. So, since it rises to the right, it must also rise to the left. The standard form quickly gives us this crucial information. Now let's look at the other powerful form, factored form. Factored form is written as a product of linear and quadratic factors. Take this function, f of x equals 2 times the quantity x minus 1 squared times the quantity x plus 3. What does this form immediately tell us? First, the real zeros of the function. By setting each factor to 0, we find the zeros at x equals 1 and x equals negative 3. A 0 is where the function's graph crosses or touches the x-axis, so these are our x-intercepts. The exponent on the factor x1 is 2. This is called the multiplicity. A multiplicity of 2 means the graph will touch the x-axis at x equals sign 1, but won't cross it. Factored form also reveals the domain. For a polynomial, the domain is always all real numbers. It also shows us the range. While this form doesn't give a specific value for the range, we know that because the overall degree is 3, the graph goes from negative to positive infinity. So the range is all real numbers. Let's extend this idea to rational expressions, which are ratios of two polynomials. Here, the factored form reveals even more. Consider the function g of x equals the quantity x plus 1 over the quantity x squared minus 1. To analyze it, our first step is always to factor. The denominator factors as a difference of squares. So our function becomes x plus 1 over x plus 1 times x minus 1. Now, we have a factor, x plus 1, that appears in both the numerator and the denominator. What does this tell us? It reveals a hole in the graph. We can cancel the matching factors to simplify the function to 1 over x minus 1. This new simpler function, which we'll call h of x, is equivalent to g of x everywhere except where the original function was undefined. So there is a hole at x equals minus 1. The remaining factor in the denominator, x minus 1, reveals a vertical asymptote at x equals 1. Factored form directly points to these crucial features. This shows how choosing the right form can be a strategic move to answer specific questions about a function. So, factored form is fantastic for zeros and discontinuities. But what if we need to divide polynomials? For that, we turn to polynomial long division. Polynomial long division works just like long division with numbers. Let's walk through an example. Suppose we want to divide x squared plus 3x plus 2 by x plus 1. First, we set it up like a normal long division problem with the dividend under the house and the divisor outside. Now we focus on the leading terms. What do we multiply x by to get x squared? The answer is x. We write x in the quotient. Next, we multiply this x by the entire divisor, x plus 1. That gives us x squared plus x, which we write below the dividend. Then we subtract it, just like in numerical long division. X squared minus x is 0, and 3x minus x is 2x. We bring down the next term, which is plus 2. Now we repeat the process. What do we multiply x by to get 2x? The answer is plus 2. We add 2 to our quotient. Multiply 2 by the divisor, x plus 1, to get 2x plus 2. Subtracting that from what we have leaves us with a remainder of 0. The result is a quotient of x plus 2 and a remainder of 0. This means that x plus 1 is a factor of x squared plus 3x plus 2, and their product is the dividend. Polynomial long division is a key tool for factoring and simplifying rational expressions. So, we just performed division and found a remainder of 0. But what happens if the remainder isn't 0? This is where long division helps us find slant asymptotes. A slant, or oblique, asymptote occurs when the degree of the numerator is exactly 1 greater than the degree of the denominator in a rational function. Let's look at the function f of x equals the quantity 2x cubed minus 3x squared plus x minus 5 over the quantity x squared plus 1. The degree of the numerator is 3, and the degree of the denominator is 2. The numerator's degree is 1 greater, so a slant asymptote exists. We find it using polynomial long division. Let's set it up. Notice I'm including a 0x term in the divisor to keep things organized. The division gives us a quotient of 2x minus 3 and a remainder of negative x minus 2. The key idea here is that for large absolute values of x, the fraction remainder over divisor becomes very small, or approaches 0. Therefore, the graph of our function approaches the line y equals the quotient, y equals 2x minus 3. This line is the slant asymptote. So when the remainder is not 0, long division helps us understand the function's behavior for very large inputs. We've covered going from factored to standard form by multiplying. But what if we need to expand a polynomial, like a plus b, to the nth power quickly? That's where the binomial theorem comes in. The binomial theorem provides the formula for finding any term of a binomial raised to a power. However, for smaller powers, we have a very handy tool called Pascal's triangle. Pascal's triangle is an amazing pattern of numbers that gives us the coefficients for binomial expansions. Each number is the sum of the two numbers directly above it. Let's use this to expand the quantity x plus 2 to the third power. Since the power is 3, we look at row 3 of Pascal's triangle. The coefficients are 1, 3, 3, 1. Now we build the terms. The powers of the first term, x, start at 3 and go down. The powers of the second term, 2, start at 0 and go up. So the expansion is 1 times x cubed times 2 to the 0, plus 3 times x squared times 2 to the first, plus 3 times x to the first times 2 squared, plus 1 times x to the 0 times 2 cubed. Simplifying the powers of 2, we get 1x cubed plus 3x squared times 2 plus 3x times 4 plus 8. Multiplying the coefficients, we arrive at our final answer, x cubed plus 6x squared plus 12x plus 8. Pascal's triangle makes expanding these polynomials straightforward. So let's quickly recap what we've learned. The main idea is that the representation of a function is not random. It's a strategic choice. Factored form is excellent for quickly identifying x-intercepts, vertical asymptotes, and holes. Standard form, with its leading term, is your go-to for determining the end behavior of the function. We also added powerful tools to our kit for moving between these forms. We saw how polynomial long division allows us to find quotients and remainders, and how a non-zero remainder leads us directly to the equation of a slant asymptote. And we reviewed the binomial theorem, simplified by Pascal's triangle, as an efficient way to expand binomials raised to a power. By understanding and applying these concepts, you can choose the most useful representation of an expression to solve any problem you encounter. Thank you for watching.